How would I simplify that? 2x y to the third Tell me what you did. The biggest fourth I can divide 32 by, which is 16, right? 16 times 2. So that's right, with one left. That's correct. That's correct. Y'all didn't have homework Friday, right? Did you? Which one? What did you have? Oh yeah. Well, give me questions about your homework then. That's better than me reviewing. I don't know why I don't have it. Thank you. The paper was easier. Oh yeah, I do remember now. Okay, number 30. Fourth root of r cubed times the square root of r. Thank you. Tell him that was not the bet. Okay, what's the base here? Just tell him 1 week. Say 1 week. R is the base. So what's the exponent on the first r? 3 what? 3 over 4. What? 1 over 2. Because I'm multiplying with the same base. Yes, you would. You add. So 3/4 plus 1/2, which Amy says is 3/4 plus 4. She's not wrong. So I get r to the 5/4. But remember, it said simplest radical form. So this is 4th root of r to the 5th. And now do your division. That's exactly right. Okay. Tell me what 34 is. Give me the problem. And if you made it what? Okay, so what you could really do here, and I'm not going to hold you responsible for this. We didn't go quite this deep into it. You could really make this the square root of 5m. You could take the square root of both of those.
I did 25 and 2/4, 25 and 1/2, 25m.
Same thing.
I got 5/3.
So, okay, 25m squared to the 1/4. Okay. 25 to the 1/4. 2 times a fourth is a half, right? Well, then what you could do is you could essentially say this is 25 to the 1/2 to the 1/2, right? Because when you raise a power to a power, you multiply. You used photo math clearly. 5 to the 1/2, m to the 1/2, which you put them together under the same. You don't have to go that far with it. Yeah. Yes. Can you tell me what it is? All right, so this is going to be the cubed root of 24. Yes. All right, so I'm going to go ahead and just take this through just because I want to expand it so I can simplify it. So I get 64x to the 4th. So now 64, 4 times 4 is 16 times 4 is 64, right? It's 4. We all agree? So the third root of 64 is 4, and then 3 goes into 4 one time with 1 left over. He said what? Okay. We'll see. 1 week was the bet. 1 week. Not the entire week, 1 full week.
7 days. But you don't think it's gonna Wednesday, Thursday, Friday, Saturday, Sunday, Monday.
I don't think his parents will let him go to the dance and then not come to school. No.
No, that. But Angela might not.
I'm just saying. Okay. So I'll say again, there's no way he's 31. 4 over the cube root of 4.
No, 4 over.
Oh, 4 over a 4? Ew. Okay, so they're the same base, right? This is 4 to the 1/3, so just subtract them. 1 minus 1/3 is... And then I can try to simplify because it's the simplest radical form. Cube root of 4 squared, which is the cube root of 16. Does that split up any? It absolutely does. 8 and 2. So 2 cube root 2. That was fun. Yeah. Give me the problem. Same thing. So this is 7 to the 3/2. This is 7 to the 1/2. If I subtract them. Anything else? I thought that was 33. No. Dozier. What's the problem? Yes. Are you confused? 27? Give me the problem. This is cube root of Dozier. Sorry. It just flips it. That's all it does.
Wait, is it still negative?
Yes, that the denominator, the flipping around like that only impacts the sign on the exponent. It's fine. So what times itself 3 times gives you 216? 6. So this is just negative 1/6. Yeah.
It's gonna happen.
It's gonna be a storm. Tropical depression.
You can remember what the game was.
You shouldn't do that, Dozier. It's not nice. Stare at your paper even longer. We have that long? Oh.
That look right to you. Does it?
I don't know. I haven't worked it yet. Oh. Well, I hope he's got some work other than what's on here because that's not even work.
I erased it 5 times. I didn't know what I was doing.
Okay. Sometimes we get tickled over things that aren't. I did that this weekend. Oh, last night, kind of basic, and then I'll throw in the transformations and show you how that works because we've done transformations. But we're going to talk about square roots and cube. Thank you. Okay, square. I don't know where the time went today. But, okay, square roots and cube roots is what we're looking at. All right. So, oh man. Y'all, this whole time, y'all didn't even tell me. I'm not even. Thank you, Ellen. There's no. That's just your homework.
There's a back.
No, there's this. So the second page is just a graphic organizer to help you. So if you want to, okay, well we'll use that. We'll use that one. We'll use the second page. Look at the second page. All right. So your parent function for the square, the one I handed to you second, the graphic organizer, the 4 squares. Oh my gosh. All right, square root. The parent graph is just the square root of x. Okay, let me show you what it looks like. So I start at 0, 0. This is my end point, or sometimes it's called a turning point if I'm in a cube root situation. But 0, 0. So see where it says end point there? That is 0, 0. And then what I do is I go up 1 and over 1 because the square root of 1 is 1. And then if I go over to, what's the next perfect square you can think of? 4. So maybe if I go over to 4, what's the square root of 4? 2. So this graph is going to look something like this. Really what it is it's half of a parabola on its side whenever you look at it. So if you turn that parabola over and had it going, that's the graph of a square root. So looking here, what is your domain of the parent graph? 0 to infinity. Is the 0 included or excluded? Included, because that is a solid dot right there. How about the range here? 0. 0 to infinity. The lowest it goes is 0, and then it goes up forever. No, because we're going to start moving these. Okay, so we're going to start transforming them. So look at the very first one, which is transformed there. Now remember, just as a reminder, let me show you transformed here, what each value does. 0, 0. I know, I'm telling you as we transform. This would be with transformations. Tell me, what does the A do? Shrinks or stretches vertically or horizontally? Vertical. This is a vertical shrink or stretch because it's out in front, right? It also has to do with my reflections. If it's positive, it's up, bless you. If it's negative, it's down, right? So this might also, if negative, then it's reflected over x. Remember that? So instead of it being above like this, it would be below like that. All right, what does the h do? Left and right, but it's opposite sign, right? And how about the k? Up or down, same sign. Okay. Now, an easy way to graph. Since I have the 0.11 on here, an easy way to graph these in transformed form is always, your endpoint is always going to be your HK. Okay? Because it shifts, if it starts at 0, 0, and you shift right to and up, you see what I'm saying? It's always going to be just those values. H, of course, is still the opposite sign, whereas K is the same sign. Yeah. Uh-huh. Yes, if it's reflected. So if there was a negative out front, then it would, no. No, well, it keeps inching up. It's just inching up slowly. Think about a parabola on its side. If this is a parabola, right? This is this half of a parabola laid over on its side. And we'll talk about why soon, but they're inverses of each other. All right. The other thing, and it only works for the first point, so I'm hesitant to even tell you what is what. I did a parabola, and I said it's really, this is just this half of it put on its side. Okay, just ignore it. Never mind. Okay. I guess that takes too long to click eraser, then click back to pencil. Okay. Now, I can look at A as kind of a slope type situation, but it only works with the very first point from the turning point. So slope, well, endpoint, from endpoint only one point. In other words, in this parent graph, right, my A is 1. So I start at 0, 0, and then if I do a slope of 1, that's up 1 over 1. It doesn't work for any other points. It only works for the very first point to do it that way. From here, the slope doesn't work that way. But here, and really all I need is 2 points to graph it. So you can graph the second point that way. Okay? Now, let's do an example and bring it all together. Look at example 1. We have f of x equals the square root of x plus 1 minus 3. And Davis already said it's left 1, down 3, and he's absolutely right. But what would my starting point be here? Negative 1, negative 3, right? Negative 1, negative 3. That's the starting point. Or end point, yeah, end point. Okay, yeah, end point, sorry. Same thing. This is just a point. It's nothing more than a point. So parentheses, yeah. All right, now I'm going to do my slope. My A is 1, right? So I'm going to go up 1 over 1, and I'm just going to connect from here. That's all I need. That's enough. I don't make you do any more points than that. We'll get into more. This is a really, really, really easy graph. Okay, so if that A in front was 2/3, then I'd go to my endpoint and I would go up 2 over 3. It's just 1, right? Yes. Now, what's your domain here? Look at that graph. What are the x values? Negative 1 to infinity. What's your range? Look at the next one. It's flipped and up 6. Everybody agree? Okay. What's my endpoint? 0, 6. 1, 2, 3, 4, 5, 6. Well, now it's a negative 1 instead of a positive 1. So if you had a negative 1 slope, what would you do? Don't go left. Down 1, right 1. Remember, it should look like it's been reflected, and it has. What's the domain? Oh, the range. Your domain and range is always based on your endpoint for a square root graph. Domain, range. You just have to decide. All right, let's talk about cube roots and I'll be done, I promise. Square and cube roots, that's all we're graphing. That's all we will graph in this class. I don't even graph them first. Not by hand. Say again? Yes, I'm sorry. All right, cube root. You thought square root was easy, cube root is even easier. Parent function, cube root of x, that's it. Yes. Okay. All right, now we have what we call a turning point, and the reason for this is cube root looks a little bit different. Remember, square roots, we can't take the square root of a negative number, right? That's why it doesn't go negative. But I can take the cube root of a negative number. And so I don't have any restrictions on the domain here. Did you say why? Well, you would think it makes it harder, but it's really not. So, all right, I call it turning points here because it's where I kind of change direction. Your turning point on the parent graph is 0, 0. Same place, right? So I'm starting right in the middle. Now for the cube root one, I'm still going up 1 over 1 because the cube root of 1 is 1. But what's the cube root of negative 1? Negative 1. So whereas the top looks very similar to a square root graph, this part comes around, it kind of looks like a stretched out S. Because you don't have any domain or range restrictions. What's your domain and your range? Every time, every cube root graph, the domain and range is exactly the same. It's negative infinity to infinity. Your A, your H, your K, your negative, all that is exactly the same. H and K still shifted left and right. The A in front still vertically stretches. So your transformation still looks like this. And your turning point is still HK. And I'm still going to do the slope just like I did before. This time I just have to do it twice. So let me show you an example. Look at the first one there. The cube root of x minus 2. Transformation language, what have I done? Right 2. Yes? All right. So what is my turning point? 2, 0. Because I've slid it over, right? So 2, 0. Correct. You did. All right. I know. In fact, I can go ahead and do my domain and range because every cube root is exactly the same. But same K. Yep. Same as it was with square root. All right. So now my slope, 1, right? And I'm hesitant to call it slope, but I find this is the easiest for students to remember. Up 1 over 1. And then I have to do the same thing in the other direction. Don't connect this like a line because it's not a line. Oh, I gotta let this one more thing. I'm hurrying. Okay, so transformation language, what happened? Left 5, up 4, vertical stretch of 2. Before I show you this, if this was, let me show you what a reflected one looks like. if this is your normal one, right, then the reflected one looks like that. There we go. Just so if you get, I know, shut up. Shut up. We're going on to this one. Okay. Turning point. Does it? -5, 4. 1, 2, 3, 4, 5. 1, 2, 3, and 4.
That one day where you were.
Domain and range, of course, negative infinity to infinity. And then my slope, but not slope, right? That A in front says 2, which means go up 2 over 1. Up 1, 2 over 1. Same thing down, down to left 1. So it should look like a line, but instead it's going to be a stretched out S. Now, take a look at your homework and let me talk you through a couple things so you know what it is they're asking. 1 through 3, that's your transformation language we talked about. And all you are doing is describing those transformations. You're doing nothing more, no graphing there. 5 through 10. So you're graphing each one the same way we did, but you're also taking in that end behavior. Remember the end behavior we talked about? As x goes to infinity, what does the graph do as x goes to negative infinity? And you're increasing, decreasing intervals. That's all I got for you.